All right, I'm back. I didn't actually even take a break. I didn't move from my seat or anything. We're going to look at the real polymorphism. And this is runtime polymorphism. And this is where things get a little wonky with C compared to all these other languages. Java and Python and all these other languages handle this in I would say, a better way. And you might be used to this by now, but C++, because of how it was invented and how it was done, there are certain little compromises with this. One of them is this form of polymorphism, runtime polymorphism. The idea is if I call paint on a rectangle, on a circle, on a shape, I expect the right function to be called. I just call paint on all three of these things, and what I would expect is that if I call paint on a Rec2400, I get a rectangle. If I call paint on a circle, I get a circle. But the underlying parent class has a different paint function. The paint function in the underlying parent class doesn't really paint anything at all. It actually just paints an outline based on what I have. So my underlying parent class just paints an outline. But really what I want is when I have a rectangle, it draws a rectangle. I want to call the right function. So in this example, just for right now, a dog, a duck, and a cat, they're all animals. If you say, or yeah, you can, let's say call them just animals. You can't call a duck a pet, really. If you tell an animal to speak and it's actually listening to you, which questionable for cats and ducks at least, but if you tell them to speak, you would expect there's no generic animal speak, right? They don't all go animal or meh, or I don't know what they would do, right? There's no generic sound for an animal speaking. Duck makes a particular sound. If you don't believe me, listen to the song What Does Fox Say? I have kids, I have to listen to that song. Anyways, right? Every animal has a different thing that they say. So when you say speak or make a sound, every animal should make a different sound. But if I just say animal, make a sound, and the animals have some kind of generic sound, every one of them would sound the same. Let's have a look at the rectangle class again, because this hopefully, let's make sure. So we're going to look at real code in a second. When I talk about printing off a doubly linked list, I would expect when I call print on it, I get the doubly linked lists version of printing something out, not the linked lists version of printing something out. Right? I don't want the, or let me think of another example. Essentially, if we don't know what type of object it is, and we just say it's the parent type, we don't want the generic format of it. So let's actually have a look at this. Hopefully it'll be a bit more obvious when we actually do this. Okay, so here we go. I'm going to compile my code. It should work. So what we're going to see here, last time around, we drew a bunch of stuff on the screen. We drew a bunch of shapes. I just clicked and dragged, drew a bunch of shapes. I made one change in my code. I changed one line in total. For between the last demo and now, I've changed one line. I have not changed anything since the last time you saw this code. So here we go. I'm going to draw a rectangle. There is something there. It doesn't highlight, but there is something there. Okay, I'm going to draw a circle. There's something there. You can't see it, but there's something there. There's something there. There's something there. I'm going to draw a triangle. What the hell's going on? Clearly, something happened in the paint method. I didn't get rid of the paint calls. The paint calls are actually being called. What is happening is that I do not have polymorphism. Let's close this up and see. It's going to, I think it may even crash. Yeah, it throws a crash, but that's fine. This is just for the demo. Here is what's happening with Shape 2400. Shape 2400, here we go. I'm going to call this paint method. When I call paint, every one of those shapes, when I call paint, it goes in here. I'm going to hit this particular line. It paints the outline. This is the generic version of painting. Oh, I want to show you this. Here's the ugly, by the way, here's the ugly version of the code if I had to manually cast everything. So the ugly version of this code, if I don't have polymorphism, is I go into Paint, I'd have a switch statement, figure out what type of shape I'm drawing. Then I'd have to go into each one of these shapes, cast it to the particular kind of shape it is, then call Paint. And every single function where I need to go through the parent and then get to the child would have to have this exact same pattern where I go figure out what kind of shape it is or what kind of object it is, then have a special call to the individual call for that shape. It would just ugly. Your code would explode in terms of size. And when I added another shape, I'd have to change it like 40 different places. What I want is it knows how to paint itself. So what is happening when I call this function, when I call paint, is I'm going into here now, instead of going into the rectangle paint method, I'm going into the generic shape paint method, which doesn't paint anything at all, just paints an outline sometimes. And that's it. If I did some kind of painting method in here, it would always paint that same way. Every single shape would look the same. That's not what I want. When I have a whole bunch of shapes, I want the shape that's appropriate to what I'm trying to draw. If it's a rectangle, it draws a rectangle. So, what the hell just happened? So, I have an array of different shapes or an array of different linked list items or whatever the case, whatever I'm dealing with at the time. I go to Paint, or if I have a bunch of linked lists, I go to Print the linked list. And if it's a doubly linked list, it should do something different than if it's a normal linked list. If I have a bunch of rectangles, it should draw something different than if I have a bunch of circles. The function, though, is determined at compile time. When I call Paint and I have an array of shapes, it says, oh, I know where that function is. It's in shape. It's not in rectangle 2400. It's in shape because I just have an array of shapes. For static binding or static resolution, static linkages, it means I bind it early. It means I figure out what the call is based off of what's in the array, right? If I don't say it's a rectangle explicitly, but I make a rectangle and I put it in an array of shapes, what ends up happening is it just calls the shape call. And unless I'm casting it first, I'm going to get the wrong version of this. Casting it first is a horribly ugly code. It has all these oh, but on a Tuesday, change this. And it means I lose information hiding. I need to know what every single one of those shapes are in order to paint it the right way. I need to know what every single child class is to make sure that things don't go wrong. So I'm going to fix this code by changing one thing. So back to the code. Let's change our code, and we'll change it by changing one line of code. Here we go. I'm going to close this off. All right. And I'm going to go to shape2400.h and the one place I changed. There we go. The grand total of all the changes, and actually I don't even need that part. The grand total change between that made all the difference in the world is literally just using the word virtual, and it's not virtual reality. I don't know where they come up with a virtual. It's a virtual table, but the keyword virtual is the only thing that changes it from a workable solution to that garbage that you saw recently. Let's compile it again. Just all I've changed is put the word virtual in there. Let's see it in action again. All right. It's going to be a circle. That's going to be a triangle. That's going to be a rectangle. All I did was put the word virtual in one place. That's it. What the hell just happened? Okay, I'm also going to point out one other thing, so let's remove that. And I'm also going to put in one other thing, which I had before. That's not going to make any difference for us. It is going to make a difference. I don't think I can even compile it right now, but let's see. It still might let me compile. I'll if I don't remember to go over this, I'll remind me to go over this. That equals 0 means something. All it's meaning is that I cannot have a generic shape. They cannot exist. Just like I do not have a generic animal, they do not exist. There's cats, there are dogs, there are iguanas, but there is no generic animal. Right? There's no generic human. Each human is unique. Well, I didn't say generic human. A human is a kind of animal. There's no generic animal type. You cannot make an animal. You can make a cat. You cannot make an animal. That's all this equals 0 is saying. For the entire object or the entire class, you cannot make an instance of that class by itself. You can make a subclass. You cannot make an instance of type shape 2400. You can make an instance of a rectangle 2400, but not a shape 2400. That's what that equals 0 equals, or it actually means. This part is the interesting one. It's a virtual table. So let's look at what the heck this actually does. Okay, so here's the idea. This is the Sprag class. The parent class is this Sprag up here. The child classes are down here. These are the child classes of the Sprag class. A child class should act differently from the parent class, depending on the situation. So if the Sprag class has a function called order drink, what would you expect? When the parent class of the Sprag class says order drink, early binding, I don't care if it's a child class or a parent class. If I do early binding and I say order a drink, I get a beer. In case you're wondering, that is Old Rasputin beer. That is 9% alcohol. It is very, very heavy. I'm not a big fan of it, actually, but I needed something strong. Okay, so when the Sprag class says order drink, you get this. If you do early binding, if you do not have a virtual function, and these are Sprags, and these are Sprags, these just happen to be a child class of the Sprag class, what ends up happening is that your kids go to the hospital because the children Sprags are going to get a beer too. The Benjamin object of the Sprag class will get a beer. What I really wanted was them to get a Fanta, right? I want them to get a pop instead of an alcoholic beverage. Runtime polymorphism lets me do this, but it requires me to have an extra little workaround. Runtime polymorphism means that on the fly, when I call order drink, I figure out which class I'm in and call the appropriate function. And it looks confusing, but it's a beautifully elegant solution for how much they painted themselves into a corner. Here's the idea. If I call virtual on a function, so I put virtual paint or virtual get area, it will put an entry into a virtual table. Every single object of this class, so PP shape, for example, will have a virtual, if I make an object of PP shape or I make an object of type rect, I will get a virtual table no matter what. So at the moment I put the word virtual on any part in my code, I will get this virtual table. This is just a lookup table. That's all it is. But I get a pointer to this lookup table and it gets generated for me for free. So I make an object of type rectangle, I get a lookup table. I make an object of type circle, I get a lookup table. And so this lookup table is on the object. The calls are based on the object itself, not the class. So it doesn't look to see if it's so when I call paint, for example, I make a rectangle. It is a shape, but it's actually under the hood, it's a rectangle. When I call paint, I go to the object itself. I go to the virtual lookup table. I go over to the virtual lookup table and say, hey, by the way, where was paint defined? Oh, paint was defined over here, and it finds it for me in the rectangle class. It figures it out when I call the function, not when I'm compiling, but at the very last second. This is why it's dynamic linkage or late binding. It figures it out when I'm running the code. So I call paint, it goes to this table, says, where's paint defined? Oh, it's defined over there, and jumps over to this paint call over here. If I have a generic shape and I call paint, it goes, hey, where's paint? It goes on the virtual table. It says, hey, where's paint defined? Oh, it's defined over here, and I go over here. If my rectangle and my shapes are going to have the same bounding area. Okay, so if I say get the area for the shape, it says, hey, where's get area defined? Oh, it's defined over here. This one says, I go, hey, get area for this rectangle. Where's get area defined? Oh, it's defined up here. If I don't define the function in the rectangle class, I automatically point to the parent class or the grandparent class, the most recent instantiate or the most recent definition of that function. So if it's not defined in here, I'll go to the parent. If it's not defined in the parent, I'll go to the grandparent. If it's not defined in the grandparent, I'll go into the great-grandparent. A purely virtual function, that's what that is. Means I don't define the function in the parent class, and or it shouldn't be able to define the function in the parent class, and I cannot, and a purely virtual class, an abstract class, I cannot actually make an instance of this class. I don't like going into virtual tables too much for one very simple reason. Number one, all you need to do is put the word virtual down. That's it, right? Understanding the mechanics is one thing, but to actually solve the problem, you just need to drop the word virtual down. That's it. Number two, though, it's a C++ specific problem. Every other language afterwards came up with more, just sort of hid away that particular specificity. So, again, a virtual table means every single class, every single object that has a virtual table has this pointer to a table that it can look up. The object itself has this hidden pointer, the pointer to a table. That table's constant, it's static, it doesn't change at all, but all objects of type rectangle point to the same table, but they have a pointer to that table. When I call paint, I will on the fly go, hey, where were you defined? And then go back and find the right version of paint. And so every single function, I call the function, I go to the virtual table, see what definition, where the function is defined, go to the right instance of it or right implementation of it. That's what a virtual table is. And the only thing you need to do is put the word virtual in front of a function that you want to make sure that it goes to the right location. I get this a lot, and I would like to I'll point it out in a second. You will see me put the word virtual in the parent class, the child class, the grandchild class, all of the classes. I'll put the word virtual. I don't need to. I only need to put it in the parent, like the highest level class, and then all of them will be virtual. I do not need to put the word virtual for paint here, but I can. The reason I want to put the word virtual on the paint right here is because I want the person reading my code, or myself 2 months from now, to remember, oh, by the way, that was a virtual function. If I leave it off, it is still a virtual function, but it's not slap you in the face obvious that it's a virtual function. If the parent class is a virtual function, then every single child class is a virtual function. But if I don't put the word virtual here, you don't necessarily obviously know when you look at the code. So I get into the habit of putting the word virtual and every single thing afterwards. That's just me. Or actually, it's a lot of people. That's a design recommendation. For virtual functions, there are a couple problems. One, the problems are found at runtime. If you do not call that function, let's say you make a paint circle, so a paint method for circle, paint method for triangle, paint method for rectangle, and you forget to test your triangle's paint method. You just forgot to test it. You will not see the problem at all. If it has a crashing bug, instead of a compile time error, like when I go to compile it, it tells me I have some kind of error, and I fix it at the time. What ends up happening is I don't notice I have a problem. I ship the code out to customers, and then suddenly it's crashing on them because they're testing it and I didn't. So the problems are found at runtime, which is a bad place to find things. There's an extra overhead. There's one pointer. It does require a little bit. It's a bit slow because I have to go to the virtual table, find the pointer, and go back again. It's like a couple operations. It's not that much of an overhead, but back in the bad old days, that used to be a big thing. And honest to God, seriously, just forgetting the word virtual in places is my common mistake. I'll design my code correctly, and I will forget to type the word virtual in my parent class's function method, and you could stare at this for hours trying to figure out why the heck this thing doesn't call correctly. And if you call everything virtual, it just means there's extra overhead and it's just uglier code. You put the word virtual on only the functions where you need a virtual function. But when you do that, it's very easy to forget the word virtual. So there are problems, but they're not critical. They're not show-stopping issues. And just because I like nerdy comic strips, there you go. So when we come back next time, I want to look at linked lists again and virtual functions again. I'll modify our linked list class one more time, and then I'll just remind you what virtual functions look like and how polymorphism works. So it's more of a reiteration of what we just talked about, just so, because I don't want to just go at a blistering pace all the way across. Okay, I'll talk to you guys soon.